Hi, everybody. I'm Noah Zentis. I'm going to talk about Rust. It's an IoT, well, not IoT specific, but it's a new programming language that works well in the IoT context. We have a lot to get into, so I'm going to start off now. So, as IoT developers, we work with constrained devices. These are small things. They don't have very much memory. They don't have very much processing power. Their connectivity is limited. They may or may very well not have any network interfaces, and they're operating on a very limited power budget. At the same time, we have to make sure these things are reliable. We have to make sure they're safe. We can't afford to just go and reflash them in the field if they break. Additional RAM uses power. Every byte of RAM that you build into your device requires yet more power while it's active. This has serious impacts on the way we build our applications. We have to keep our data small. We can't store very much stuff. We have to avoid making a bunch of copies. Ideally, we can keep some data out of memory at all. Again, same thing with the processor. We should keep the devices asleep as much as we possibly can. What that means is not just that we do little work, it's that we do as much work as possible in the shortest amount of time. If your function runs within a millisecond, that's great. But if that function runs in a microsecond and you have to run it just as often, that means you've saved a significant amount of energy. And more than just speed, we want to make sure the performance is predictable. We want to make sure it's consistent. Every time the interrupt goes, we want to make sure that our code will run in approximately the same amount of time. Now, as I said before, these need to be reliable. These are devices that people depend on. People depend on these devices for security, for their health. They depend on them to make sure that the physical infrastructure doesn't break down. We have to know that these things are reliable. We have to know that they handle all of the cases. We have to know that you're not going to get a runtime exception because you used the wrong type of value when you're trying to restart somebody's heart. These things matter. But now that we've established that this is important, that reliability matters in this context, I'm going to talk about language design. So, as far as languages that you'd use in an IoT context, there are two main approaches. First one is building languages that are higher level C or C++. So Java is a good example of this, right? Something that's a little bit higher level. It's not quite as performance intensive, but at the same time, it's somewhat more safe. The other approach is to move down from Python or JavaScript or Ruby or something like that, where you take a dynamic language and make it faster and more performant. Go does this, right? It's Google's language. It's primarily intended as a easier C for Python developers. Lua is another thing that does this sort of thing along with LuaJIT. So it compiles to native code at runtime and it's fairly efficient. It's not terrible. Rust fits into the higher level C category. Now, it's slightly more complicated than this, but I'll go into that in a bit. So why build a new language? Why not use something that already exists? No other language that currently exists hits all three categories of safety, performance, and predictability. Low-level languages like assembly and C, you can get immense performance, right? Hand-optimized assembler is the gold standard for making things fast. C, operating systems are written in it. It's one of the fastest compiled languages around. But at the same time, history has shown that we cannot write safe C or assembly code. There are always bugs. Something like Python, it gives you safety and predictability to some extent. Your code is relatively predictable, and you know that it's not going to crash randomly, assuming that you have good unit tests, but it's not exactly fast. Go or Java, they're both safe and relatively fast, but you can be interrupted at any given time for garbage collection. You have no idea whether that will occur. Rust does all three. Now, I'll talk about why in a minute here, but it gives you safety without having to deal with the random performance penalties of garbage collection or additional runtime checks in most cases. So as far as benefits go, Rust gives you performance that is similar. I say similar because different compilers will always generate code that's differently performant. Clang generates different code from C++. C++'s compilers generate different code from something like Swift, etc. But it's similar. It's comparable to the point where there's not a huge difference. It also gives you no memory errors. This is back to the safety point that I was talking about earlier. Now, memory errors are things like writing over the end of a buffer or dereferencing a null pointer in C. These are things where you're accessing a region of memory that is something that you're not expecting, and you're introducing undefined behavior because of that. These are the single largest source of security bugs in any C or C++ program, and something like Java is still susceptible to null dereferences to some extent. Sure, it throws an exception, but it's still a failure. Go, it doesn't get rid of any of these. You can still have seg faults in Go. The only languages that really eliminate them are things like Python, where you can't do memory errors because you don't have any pointers. Rust also eliminates data races. So when you're writing concurrent or multi-threaded code, you're trying to do a bunch of things at once, and you accidentally access the same element from more than one thread at a time, and that introduces undefined behavior. This eliminates that at compile time, statically. And it has a strong type system. So something like Python that's dynamically typed or duck typed, it doesn't really have a strong type system. The types aren't inferred at compile time. Something like C, C++, or Java with somewhat stronger types, they're statically checked, but you can just kind of cast between them at any given point. There's no guarantee that a value you're expecting to be of a given type is actually of that type. Rust makes stronger promises. Rust code, you can absolutely guarantee that if you expect a value is of type A, it is of type A. Nobody can cast things to that type randomly unless you provide them an interface to do so. This lets you implement very, very strong safeguards against misused APIs. For example, the file close operation consumes the file. You can't use a file after it's closed because the file no longer exists. That's defined in the signature of the close function. Now, normally, you would expect a strong type system to involve a huge amount of compile time and programmer overhead. You'd have to write out all the types. It would be very annoying, except it's not. If you're coming from a language like Haskell or Kotlin, you've probably experienced this a little bit before. The compiler can infer types in many cases. So just because every expression has a type does not mean that the compiler can't figure out what that is without your help. If you used C++11, it's sort of like the auto feature, but significantly more powerful. It infers the type of an expression from the context in which it's used. Now, as far as coercion goes, most languages will automatically perform type coercion between different disparate data types. For example, if you have a byte and you want to interpret it as an unsigned size value, you can just use it and the compiler will automatically convert it. Or if you have a float and you wanted to use it as an integer, you can do the same thing. Rust does not let you do that. In Rust, you have to explicitly convert between any two types in order to use them. Now, these conversions are checked. So let's say that you're converting between a 32-bit integer, so range of 0 to 2 billion, and an 8-bit integer, range of 0 to 255. If your integer is 1,000, and you try that conversion, it'll fail at runtime, because there is a runtime check inserted there automatically. However, if you're converting from the byte to the 32-bit, there's going to be no check, because the language understands that that conversion can't fail, and thus eliminates the extra cost. Now, I mentioned earlier that Rust provides a lot of nice safety properties. Sometimes you have to do very weird things with memory. Sometimes you have to resort to low-level hacks that really aren't safe, but you're doing them anyway. There's a facility for that. It's called unsafe code. Now, Rust makes a distinction between safe code, what you normally write, and unsafe code, the sort of low-level hacky nonsense that you do in C or assembly. Now, in safe code, all of those safety properties I mentioned earlier, they apply. You're guaranteed that nothing fails as long as all of the unsafe code in your program is behaving correctly. That's the caveat. Now, the standard library provides many, many unsafe functions with safe interfaces, so you can be reasonably confident that your code is not going to break, and you can avoid doing things with unsafe code in many cases. But in case you need it, you have an escape hatch. You can say, oh, I understand that this is safe. I can access this variable from multiple threads. I know it's safe. I can just write to that chunk of memory because it's a memory mapped I/O port for SPI, and I need to talk to that device. You can do that. The difference between C, C++, and Go, and Rust is that all of the other languages are unsafe by default. In every case, you don't actually know whether the operation that you're doing can break everything. In Rust, you do. In Rust, safe is the default. 99% or all of the code of most large Rust programs is safe. Unsafety is extremely rare, and you really don't need to dip into it very often. Now, as far as how these safety guarantees are maintained, there's a system called lifetimes. Essentially, the basic concept is that the lifetime is a region in which memory reference is valid. So if I'm creating a variable and it's on the stack, so it's defined within a function, and then I do some other things after that, the lifetime is the region from that variable being defined and the end of the function, because after the function's exited, it doesn't really make any sense to reference that variable anymore because it's not there anymore. It disappeared. Whereas if I define a global constant, the lifetime of that is the entire life of the program. You can reference it from any point and it's safe. Now, what if you have a pointer to a structure that contains other pointers? Those inner pointers' lifetime is dependent on the outer pointer's lifetime. You can nest lifetimes. So if I have if I create a new object and it creates objects inside of itself that are then deleted when it goes away, references to the inner objects are bounded by the lifetime of the outer object. The inner ones can't outlive the outer object. Now, what this means is that since these lifetimes are checked at compile time, they are statically analyzed and inferred, the language guarantees that a pointer cannot outlive the object it points to. What this means is that you can't have use after free bugs, because after it's freed, you don't have a reference to it anymore. You can't have nullity references because references can't be null. Lifetimes provide a lot of static properties that mean our programs are safer as far as their memory behavior. What this also lets you do is enforce API semantics. So the file example that I mentioned earlier, the file is consumed by the close function, which means that its lifetime ends after the close function returns. So you can't reference that file anymore after that file is closed. Or in this example, after an iterator over its lines is created, the file can't be closed until the iterator is also destroyed, because otherwise the iterator, which has a dependent lifetime on the file, wouldn't exist anymore. Here's an example where X is this file. You can see the green lifetime there on the outermost block. All of the other inner lifetimes are contained within it. You're creating an iterator over all of the lines of the file, here, the yellow lifetime, which is then consumed as soon as you handle the error, right? You use the question mark operator to handle the error, which consumes the previous object and converts it into a new one. So a new lifetime begins there. And if you look at all of the references of variables within this program, each one has its own associated lifetime. And that lifetime is bounded by the lifetimes of any references it contains. For example, words couldn't live longer than it is right now, precisely because it operates over lines, right? The read lifetime. It can't outlive the read lifetime, so it has to stop there. If you tried to extend that down below the for loop, the compiler would actually complain at you. It would say this is invalid. In addition to lifetimes, Rust also implements, as part of its type system, a mechanism called traits. Now, a trait is a unit of functionality that can be implemented by a type. What this means is that you can have something like a string that would implement the ordered trait, because you can compare two strings and see whether one comes first or the second comes first, lexicographically, or you can compare them for equality. Now, this is not exactly the same thing as a class. Traits don't contain any data on their own. Traits are more like interfaces than anything else, except they're slightly different because with an interface, you have to define that a class implements that trait, or interface in this case. You have to say, when you're defining your class, this implements these things. Whereas with traits, you don't have to do that. You can define a trait anywhere and implement it for any type. That gives you a lot of very powerful features. Example here. Let's say that I'm defining that I have some network socket that I want to support, and it doesn't have read or write implemented for it like files or memory buffers do. Well, the obvious answer would be I have to implement read or write for that, so I can use it with all of these other functions that require read and write. The way you do that is you just say, okay, here's my implementation of read for my network socket. And the language is fine with that. You can implement a trait for a thing at any point. It doesn't necessarily need to be as part of its initial definition. Now, what this also means is that you can bound generic functions and structures on traits. So in this example, the display operation is required in order to print a thing, which makes sense, right? They wouldn't make any sense to convert something to a string and display it at the console if you can't actually convert it to a string. Equivalently, for sorting, you need the ord trait so that you can actually compare it and sort the thing. What this also means is that, generally speaking, functions will operate over the most generic possible version of themselves. So if you're trying to create a path and reference something in the file system, you don't have to pass a string to that. You can pass anything that can be converted to a string, and there's a trait for that. What that means is that it feels like it's polymorphic. It feels like there's the sort of runtime polymorphism you get with something like Python or Lisp, but it's not. It's all statically checked and it's verified at compile time. Another part of Rust that is extremely useful is zero-cost abstractions. So in something like C++, you would wrap an underlying structure with an object that would consume some memory, but you'd get some safety in exchange. In Python, you'd wrap an underlying structure in an object, and then they would spend time translating to C and back and memory for additional object overhead and everything else. Now, Rust doesn't do that in general. It shifts that cost to compile time. You spend additional compile time in order to have less cost at runtime. This is a common pattern as far as Rust code goes. Now, you can write Rust abstractions just like you might with C++, but the fancy part is because you have this type system that's extremely powerful, the compiler is able to take those abstractions and boil them back down into something that's not actually, it doesn't have any actual runtime cost. It generates the same code that you might get if you didn't use the abstraction at all. Now, I have an example here. This is just a very simple program, sums the numbers from 1 to n in both Rust and C++. Now you can see Rust and C++ both generate basically the same code. Rust's a little shorter. That's because it's using a different compiler, but it's functionally the same. I adjusted the compile flags on these two so that the comparison is fair. By default, Rust compiles in debug mode, so there was some additional stuff you have to specify to turn that off. But basically, they're the same two things. And you can see if you look at the code, the Rust version is significantly more abstracted. You're saying 0 to n sum rather than actually writing the for loop. This is what I mean. An iterator is a very high-level abstraction that the compiler is entirely boiling away and converting into the same code. For comparison, another language with similar objectives as a systems language, like Go, not quite as performant. Here, the code is less high level. You're not using an iterator, you're just using a for loop. And the compiler generates a lot of additional garbage because you have to deal with the runtime and garbage collection and thread scheduling and everything else. With Rust, you don't pay those costs unless you explicitly ask for them. It's much like the C++ idea of unless you actually use a given feature, you don't pay for it. So relative to the C++ code, you get the same performance because it's ultimately the same code when you get right down to it, but you have the additional safety of types, lifetimes, static checking, better generics, and your code's easier to reason about because it's more abstracted. I mean, iterators and mapping and filtering are these high-level operations that it's very easy to think about your program within these contexts. Whereas with C++, juggling arrays and vectors, not quite so easy. Ultimately, you get fewer bugs and you write your code faster. Relative to something like Go, you have better performance, your code's safer, uses less resources. In general, the only advantage that you get from something like Go is that it's easier to approach if you're coming from something like Python, where it's garbage collected, there's no type system really. Essentially, it's less thinking. And I don't mean that in a bad way. Rust is focused around the idea that you have to get it right the first time. Go, Python, and their family of languages is focused around the idea that it's better to do it quickly than to get it right. They do very well with that, right? You can build very fast systems, but ultimately, it's designed around the idea that it's easier to watch it fail and then debug from that than to prove that it's correct. Rust tries to shift as much of the burden as proof as possible to the compiler so that you don't have to deal with all of the nonsense that you probably dealt with in school where you were trying to prove programs correct. You don't have to do that here. The compiler will do it for you, for the most part. Ultimately, Rust compared to Go gives you more powerful abstractions because, I mean, Go doesn't have interfaces. Go doesn't have inheritance. You can't do traits in Go. It gives you fewer bugs, more powerful abstractions, and it's ultimately faster, right? This is significantly larger than the Rust version. Now, Java's not really a fair comparison because they're aimed at two different markets, but you see Java a lot, so I wanted to make sure that we covered it. Compared to Java, you get equivalent or better because it can hit C++ equivalence in some cases, but not always. It doesn't require a garbage collector or a JVM and all the additional memory usage that requires. It ultimately has better abstractions, unless you're using like something like the absolute latest Java, which most people aren't, particularly in an embedded context like IoT. You're running on a tiny device, you probably need a tiny JVM, which probably doesn't support the latest and greatest features. And you get better compile time verification. Java has checked exceptions, sure. Java can't statically verify that you'll never get a null pointer exception over the entire lifetime of your program. Now, I mentioned that reliability earlier. We need to make sure that these IoT systems are safe, that they're secure. Rust code and all of the static verification that it does proves that your code is immune to all of these additional security problems, right? So if anyone remembers the dirty copy on write Linux bug, where as part of process duplication, it was storing one copy of something rather than two, and there's a race condition in making an actual additional copy, which would let user processes overwrite internal kernel structures. That's a race condition. That's a data race, and Rust prevents that. Something like Heartbleed in OpenSSL, where you're reading over the end of a buffer. memory error. Rust prevents that. The famous macOS go-to-fail SSL bug where certificates just weren't checked. That's an unchecked error condition. Rust error handling system statically prevents that. For so long, we've been saying, oh, we can avoid security bugs in our C++ code. We just won't do all of these things, all of these thousands of pitfalls and possible traps. That clearly isn't working. It's obviously not successful because we still have these security bugs. It makes so much more sense to have the machines that never actually make a mistake and never overlook things verify that our stuff is correct than it is for us to do it manually. As I mentioned earlier, we're running in a CPU and memory constrained environment. We can't afford the performance cost of something like Python or Lua or Java or Go, where you have this garbage collector that takes additional processing. You have runtimes that take additional processing. You have all of these extra things. We can't afford to pay that cost. Or if we can, we are losing out because of it. You're using power. You're making your device more expensive because you need a bigger CPU and more memory. Rust avoids manual memory management entirely without using a garbage collector because once a lifetime ends, it can automatically delete stuff because it knows that that object is no longer used. This means that it has the same sort of automatic memory management feel as a JVM language or something like Go, where it feels like it's garbage collecting, but it's not. You can prove at compile time that your program's memory usage is bounded. It gets you the same speed as native code, rather than something like Python, where you have to deal with interpretation overhead. Nope, this generates the same code as C++. It's suitable for real-time systems, specifically because it doesn't have these memory penalties. It doesn't have these runtime penalties. You can prove that your Rust code will run in a constant, bounded amount of time. That's what you need in a real-time context, and you can't get that from Go, Python, or Java, any of these languages with garbage collectors. You have trouble getting it from C++. It's possible, but it's hard because you never know when you're going to run a destructor and a gigantic stack of them is going to occur. Rust has built-in concurrency support. Every single modern CPU is multi-core. Well, I say every single, unless you're something like a microcontroller, but the vast majority of them are. And our languages are still sort of tacking on concurrency as a secondary thing. Rust builds this into the standard library. It checks your concurrency code at compile time. It gives you confidence that your 10,000-line program has no concurrency bugs whatsoever, which is something that you can't say for any other language. In addition to that, it's built on the standard C++ compilation infrastructure. It compiles with Clang, so as Clang gets faster, your program gets faster. If you're using Rust initially, you're going to run into a lot of compilation errors. The compiler is going to spit your code back at you and say, hey, this is wrong. Now, it can feel adversarial at first. I'd like to reassure you that it's not. The compiler is your friend. Have you ever waded through some extremely complex chain of logic to find a missing semicolon at compile time or at runtime? If the compiler had just told you, it would have saved you 4 hours of work. It's always easier to find a bug when the compiler gives you this big red error message pointing to exactly where the problem is than it is when you're wading through the runtime state of your program in a debugger and trying to figure out what went wrong. It can feel like you're fighting the compiler, like you're fighting the borrow checker, which is the component that verifies that all lifetimes are correct. It's not. You're not fighting it. It's helping you. It's telling you when there's something that will fail at runtime at some point, and it's saving you that 4 hours. The compiler is there to help you. Now, I'm going to go over a few compile errors and explain why they're occurring, even though they might look confusing initially. So this is a simple program. it just assigns every element of an array to the first one. The compiler says, no, you can't access the array immutably while you're iterating over it, because you're creating an immutable reference to the array as part of your iterator, but then you're trying to access the array mutably. That doesn't make sense, because the first time around, the first iteration, that operation is undefined because you're trying to access something mutably and immutably at the same time. That doesn't make sense. The compiler is telling you that that's wrong. The way you fix it, use a temporary variable. Don't access the array immutably or mutably. Now, you could also fix this by using a mutable iterator. So in this case, you're always assigning to the first element of the array. If that weren't the case, if you were trying to modify each element in place, you'd use the iter_mute method, which would give you a mutable reference to every element rather than an immutable one. Same basic concept, but again, the compiler's error message is there because you messed up. It's trying to help you find your problems before runtime happens. Another example. This is, again, a simple program. Multiplies the numbers from 0 to 10 by 2 and prints the resulting list. Now, this one is less of a user error and more of a limitation of the language, but it can't always infer everything. I mentioned type inference earlier. It is ultimately statically typed, and it can't always get everything. It's saying it can't infer the type for items. It can't figure out what type items is supposed to be. The solution is add an annotation. Tell it, items is a vector of values. And once it knows that it's a vector of values, it can figure out the rest, but it just needed a hint. Now, Rust has a large ecosystem. So Cargo is Rust's package manager, build system, and documentation tool. If you've ever used NPM or pip or Ruby gems, something like that, you'll know exactly what this is. It's the same basic concept. It supports semantic versioning, dependency isolation, local and remote builds, and it integrates well with other tools. It's extensible. Crates.io is the website that all of the open source libraries are uploaded to. Again, it's analogous to all of the other languages' large centralized repositories of code. In addition to tools, there's also documentation. Rust is quite possibly one of the best documented languages I've ever used, other than something like Java. The core development team puts out extremely high-quality introductory materials and reference data. So if you're approaching from a Python background or from a C background, they walk you through all of the components that you need to know, all the things that might be confusing or hard to understand at first. And there's a lot of people in the community that are willing to help. The Rust community is an extremely positive and welcoming place. In general, Rust users are some of the more helpful people on the internet that I've run into. In addition to having a large library ecosystem of its own, it also supports easy integration with other languages. So Rust code is ABI compatible with C, Application Binary Interface compatible. So you can foreign call to and from Rust code transparently. There's zero additional cost to doing so. What that means is that all of the libraries that you would use in C or Python are accessible in just the same way they would be if you were writing C++. That's extremely powerful. And it just so happens that somebody has probably written a binding already for the library that you want to use. If you want to access zlib, for example, or libpng, somebody's probably already written that binding for you. You don't have to do it yourself. You might want to know how to get started. Well, Rust provides tools for that. There's a program called RustUp that's an automatic toolchain setup system. So if you just download it, install it, and then you can say, okay, I want the default stable release. It installs it for you automatically, locally, no admin privileges required. Create a new project using Cargo, and then tell Cargo to compile and run your project. This takes about like 30 seconds at most. Now, I'm not going to do a demo here because I'm not sure how well the conference platform would deal with my terminal, but if you want to follow along, feel free to ask me questions. I'd be happy to help you with any issues that you run into. As far as additional resources that you might need for learning Rust, here you go. The official website has documentation, links to libraries, links to high-quality code bases that you can use as reference. Crates.io, great place if you want to search for third-party community libraries. All of them have documentation in general. There's always the documentation is auto-generated and hosted. If you've ever used something like Doxygen or Markdown for generating documentation for your code, Rust includes that by default. The same sort of doc comments that you'd use above a function in Doxygen, Rust supports those by default, and when you package your crate, it gets automatically uploaded in the documentation. It gets generated on the fly. And then there's the official developers Learn Rust book. It covers most components of the language, although there's a few pieces that are still not documented great. Everything that you need for learning initially is there. All right, well, thank you. If you have any questions, I'd be happy to answer those now. Yes, currently Rust supports x86 by default. There's also some community projects that are creating support for some microcontrollers, like I believe the PIC, if I recall correctly, is supported by a community project, but it's not official. It also supports ARM by default. And I think there's also support for the web platform with Emscripten, but that's less IoT related. As far as operating systems go, it has first-party support for Windows, Mac, and Linux on x86. That's x86 64 and 32. There's support for ARM, Linux, Android, and I'm not sure, but I think Windows ARM might be supported too. All right, thanks everybody. Enjoy the rest of the conference.